Welcome to Explore Embedded. In this tutorial, we'll discuss about the interrupts. We'll talk in depth and in detail about interrupts and with respect to 8051. Now, what are basically interrupts? So, the processor it has say this is a processor and it wants to do n number of tasks inside it. Say it wants to work on some data or process some data, and in the meantime it also wants to handle requests from external devices. Now instead of processor going to each one of the device and asking whether it needs some kind of service, this method wherein the processor goes to each of the devices and asking whether it requires any kind of service, it's called polling. Now this would not be much efficient because the processor will not be able to do its own task or the main job it is required to be done. Now instead of the processor asking for devices if there is any work, what the processor can in fact do is it can do its own job, and the devices which require the attention of the processor interrupt it. So if they interrupt its execution, what it does is it goes to the process that has interrupted, it executes that, and then it comes back and resumes its work. Now we'll discuss interrupts with respect to 8051 today. Now if what are the sources of interrupts in 8051? The interrupts need not be external always. They could be internal interrupts as well as external. In the 8051 microcontroller, the internal interrupts are, so basically the internal interrupts are related to timers. So the timer 0 generates an interrupt, timer 1 as well generates an interrupt. So we have seen in the previous videos all the modes that the timers work on. Now an interrupt is generated with respect to timers only when a timer overflows. Like say for instance, in 16-bit mode, the timer counts from 0 to the power 16, and then when it overflows, it generates an interrupt. It could be timer 0 or timer 1, and this is mode 1 if you remember. It could generate an interrupt even in mode 0, where it counts from 0 to 2 to the power 13, which is 8192. So once it exceeds this count, it generates an overflow which causes an interrupt. Now so basically there are two interrupt sources which are internal to 8051. There are external interrupts which are called INT0 and INT1, and these are physical pins on the microcontroller. So if you remember the pin diagram, pin 3.2 and pin 3.3, these are sources of external interrupts for the microcontroller. Now apart from these two, there is also another internal interrupt which is caused by the serial communication or the UART. Now this interrupt, we can call it as serial communication interrupt. In the core 8051, this interrupt is generated after transmitting a byte of data or receiving a byte of data. So this we have discussed in the serial communication. Now this also can be used as an interrupt source. In 8052 versions, even an SPI communication generates the same interrupt. So basically we can call that as a serial communication interrupt. So if we look at it, so there are 5 sources of interrupts for 8051. 3 are internal to the processor and 2 are external. So And there is also one more interrupt, which is if we consider reset as an interrupt. So this is one more. So in total there are 6 interrupt sources for 8051. Now let us look at the vector table, or the table which decides which interrupt is placed where in the ROM location. Now if your ROM is flash, or it could be any other type of ROM as well, so for example 889S52 has a flash memory. So in the flash memory, this interrupt vector table, it decides where these interrupts are located. Now if you could observe, reset is right at the beginning, which is 0 0. It means if we reset the microcontroller, and the program counter points at the 0 0 location. Now if you could observe, there are only 3 bytes between the reset interrupt and the next interrupts. So these 3 bytes could only be a jump instruction where the actual code is stored. Now and once we have a reset, when we reset the microcontroller, that is to be done on pin 9. So if you remember, the pin 9 is a reset pin for the microcontroller. Now once this is reset, the flag for the interrupt is auto cleared. Now the next interrupt is the external hardware interrupt. So this is INT0 and this is pin 3.2 as stated earlier. And here you could observe that there are 8 bytes between 3 and 0p. So here you could write a small program, indeed if it is very small, or this again points to a location where the actual interrupt service routine is. Now by the way, the code that is executed when an interrupt is generated is called the interrupt service routine. So again in this case the flag is auto cleared, and this we will discuss a little later. So the next interrupt is the timer 0 interrupt. So as discussed earlier, whenever timer 0 overflows, this interrupt is executed and its address is 000p. And similarly, the address for external interrupt 1 is 13 and it occurs on pin 3.3. Now this is again internal timer 1 interrupt whose address is 1b, and so since it's internal, there is no pin to it, and this is auto cleared. And for the serial communication, the interrupt address is 23 and it is again it needs to be cleared by the user. Now let us go ahead and look at the registers involved in with respect to interrupts. Basically there are 2, but we'll see at the one important register here. This register is called the interrupt enable register. Now the D7 bit, it's the global interrupt bit, or if any interrupt needs to be active, this bit needs to be 1. So when dealing with interrupts, or when we want to use interrupts, this bit should always be 1. Now ET2, this is only available in 8052 or higher versions, and this bit needs to be set to 1 if timer 2 overflows, right? So this is only with 8052. And ES is the serial interrupt. So if you want interrupt to be generated on TX, or transmission or reception of a character in serial communication, this bit needs to be 1. So now the next bit is for the timer 1. So if timer 1 overflows, an interrupt is generated, and if you want that, then we set this bit to 1. So next is an external interrupt pin, and this is EX1, so that would be port 3.3. so if we want an interrupt to be generated on pin 3.3, this bit should be turned on, or this bit should be 1. So next is similarly, this is timer 1 and this is timer 0. So we had an external interrupt on pin 3.3. if you want an external interrupt on pin 3.2, 2, this bit needs to be 1. So basically the thing to remember here is whenever you want to turn on any interrupt, we should configure the external enable interrupt enable resistor in the 8051. Let us move ahead and look at a timer interrupt example. Now if you remember our example on timers, we had done example wherein we would generate a delay of 50 milliseconds using timer 0 in mode 1. So mode 1, if you remember, it's a 16-bit mode wherein we can count from 0 to 2 to the power 16. Now if you remember, in order to use a timer, we need to configure the TMOD resistor, and for timer timer 0 mode 1, it would be 0x02. And next what we do is we turn on this timer, we load the TH and the TL with the respective values. So to generate a delay of 50 milliseconds, we load appropriate value on this. So what we do with example on timer 1 is so there are basically two things that we do. And now let me draw a small diagram here. Okay, so what we have done for the timer example is we have connected a couple of LEDs to port 3. This is 6 and this is 7. So we have connected a couple of LEDs to port. Let me just write that clearly. So we have connected a couple of LEDs to port 3.6 and 3.7. And there's also one more LED here. Alright, and this is ground. And there's a switch which is connected to port 3.2. So this is the switch. Now what we do is we read the status of the switch on port 3.2 in the main program, and we show that on the LED port 3.6. So what we do is, when the switch is, so basically this is pulled high. So this switch is pulled high. So whenever it is off, we get a 0, and we get a 1 whenever it is turned off, and we blink or we turn on the LED which is connected to port 3.6. So we read the status from port 3.2, which is a switch, and show it on port 3.6, which is LED. So we do this in the main program, and we use the timer in an interrupt mode where we configure the timer to generate delay of 50 milliseconds. And what we do is, on every 50 milliseconds we toggle the LED on port 3.7. so this LED is toggled. Now what this does is, whenever the switch, in the main program, so let me just write this. So if we start here in the main program, what we do is we monitor the switch and display it on LED, and then we stop. So that's all we do in the main program. But whenever an interrupt occurs, what we do is we go to the interrupt routine and we check the what the interrupt. We get an interrupt only when the timer overflows. So when a timer overflow interrupt occurs, what we do is we blink or toggle the LED which is connected to port 3.7. so what we do is, so say this is LED, 2, what we do is we toggle the LED. So what this does is it blinks this LED continuously, and what it does is, so whenever we press a switch, that switch status is displayed on LED connected on port 3.6, and this is toggled continuously. So the point here is, so whenever we configure an interrupt for timer, and in real time if we press the switch, it appears that the LED is blinking continuously, and even the controller is reading the switch and displaying it on the other LED. So so if you see it in real time, you can observe that both the tasks are almost parallel. So the LED is blinking all the while, but in the meantime when you press a switch, it is also shown on the other LED. So in this you watch a short demo, and then we look at the code. Now if you look at the code, it is pretty simple. So one thing to observe here is whenever we want to write an interrupt routine, interrupt service routine, it is again a simple function, but that needs to be inside a file where you have the main program. And the first thing that you note here is the keyword interrupt. So this name can be anything. So timer 0, since we are using timer 0, we are given an appropriate name as timer 0, but the interrupt, and also observe the interrupt number carefully here. Now if we go back to the interrupt vector table which we had seen earlier, so we have written the interrupt numbers on the right hand side here. So if you are writing it in C, the interrupt number should match the interrupt that you are using. So for external hardware interrupt, this is 0. For timer 0, which we are using in this case, the interrupt number is 1, and we'll see these two later. We'll be using external interrupt, hardware interrupt, and there are two hardware interrupts, and the timer interrupt. So we'll not be using the timer interrupt though, so we'll be using the external hardware interrupt 0 and external hardware interrupt 1. So, and for now what we're using is this. So this number needs to be 1 here, so that you could observe in the code. Let's go back. Okay, so this is the number. Now let us start with the main program first. So we put the timer in mode 1, and it's 16-bit timer. We load it with value 4B and FF. So if you're not familiar with this, you can watch the timer video. So it generates a delay of 50 milliseconds. So what we next do is we configure the interrupt enable resistor. Now if you remember that the last bit is EA, so this is turned on, and then this is don't care. So let me just go back again. Okay, so if you look at EA, we want the the timer. So the EA is 1 in this case, all these bits are 0, and we want the timer to be 1, so timer overflow interrupt to be 1. So this becomes 8 and 2, so in hex it would be 82. So let me just take you back here. So okay, so hence we have put IE as 82 in this case. Now and what we have done is, as I told you earlier, there are two LEDs, both of them are connected to 3.6 and 3.7. So what we do is we'll blink the LED which is connected on port 3.7, and the switch connected on port 3.2. we will take this switch and we'll display it on LED 1. So this is defined as switch 1 and this is defined as LED 1. So what we do in the main program is we'll read the switch 1 and display it on LED 1. So it is pretty simple. So in the main program, so for all the while it does this, right? So since the switch needs to be an input, we send a 1 initially, and then we turn on the timer. and we want to turn off the LEDs, hence we turn them off initially. So what it does is it continuously reads this particular switch and it shows on the LED. That's all it does. But the interesting part here is, since we have turned on the timer here, since we have turned on the timer 0, what it does is whenever the timer overflows, the interrupt service routine is called and this is executed. And what happens here is we have toggled the LED. So what you could see here is this LED 2 is not of LED 2, which means if it was 0 earlier, it would be 1. And we again reload the timer for this to be 50 milliseconds, and again it goes back and keeps reading the switch. Now in the real time, if you see, what happens is you see the LED 2 to be blinking continuously with the timer interrupt, and then whenever you press switch 1, you as well see it on LED 1. So this you can watch it in the demo. Alright, so let us go ahead and look at the external interrupts as well. Now we have seen that the sources for external interrupt are pin 3.2 and pin 3.3 on the microcontroller. Now again, what we do with an example on interrupts is, so we have connected two switches. The switches are connected to port 3.2 and 3.3, and similarly we have two LEDs on port 3.6 and port 3.7. so this is switch 1, this is switch 2, this is LED 1 and LED 2. Now what we do here is whenever we have an interrupt, external interrupt, we turn on the LED, turn on the respective LED. But before we go ahead and look at the code, let us see at external interrupts in a little detail. Now there are two ways in which external interrupts could occur. The first is called level triggered, and the second is called the edge triggered. So what we mean by level triggered is, say if port 3.2 for instance, if there is a low level or a low signal on this pin, if this is 0 and this pin, then an interrupt is generated. So on 8051 there is only low level triggered interrupt, so there is no high level triggered interrupt. There is no interrupt if the transition occurs from 0 to 1. So there is no interrupt for this. So there is only low level triggered interrupt. And there is one more type of interrupt which is edge triggered. So instead of detecting an entire low level, what it detects is it detects the transition from high to low. So this we'll discuss at the end. Now let us assume that we are using the default mode wherein it is configured as level triggered interrupt. So there is, by the way, one more resistor which we have discussed in the timers, which is called the TCON, and there are 4 bits which are specifically specify whether it is a level triggered or a edge triggered interrupt. We'll see this at the end. Now assuming that this is a level triggered interrupt and the switches are connected to 3.2 and 3.3 and LEDs are connected to 3.6 and 7, what we do is we in the interrupt service routine we read the status and simply display on the LEDs, and we do not do anything in the main program. So this is all out of the main program. And we could also remember that the switches, they are always pulled high. So this is port 3.3 2 for example, and there is a switch connected here, and this switch when it is open there is always 1. So this line would be always 1, and whenever we press the switch it gets a low level and this triggers an interrupt. Alright, so let us go ahead and look at the code for this. Again, if you would remember from the previous discussion, for external interrupt 0, the interrupt number is 0, and for external interrupt 1, the interrupt number is 2. So for then and we use the interrupt number 0 for the timer 0 interrupt. Now what we do here is very simple. So you define two LEDs on 6 and 7 and two switches on 2 and 3, port 2 and port 3, port 3.2 and port 3.3. Now as you can see here, there are two interrupt service routines. First one, it turns on the LED 1. So interrupt 0, it turns on LED 1, and interrupt 2, it turns on LED 2. So this is pretty simple. In the main program, what we do is so as this, you should be familiar with this now. So whenever you want to read switches, we make it 1, and whenever we want to make that pin output, we make it as 0. Then we turn on the global interrupts with EA bit. In the previous example, what we had done is we had configured the entire register IE in one go. In this case, we are setting individual bits. So just to show you, it can be done in two ways. So we turned on the external interrupts. We turned on the global interrupts. Then we turn on the external interrupt 0, external interrupt 1. And what we do in the main program is just turn off the LEDs. Turn off both the LEDs. So you could write any other code here as well, and these interrupt routines could be anything and not just switches. So if we go ahead and look at this demo, what you see is whenever you press a switch, the LED turns off, and neither of that we are doing turns on. So neither of that we are doing in the main code. So it is all handled by the interrupt service routines. Alright, so you can go ahead and watch the demo for that. And so we have in the beginning we said there are two kinds of interrupts. One is edge triggered and the other is level triggered. And if you remember the discussion on timers, we had told that TR0 it runs timer 0, TR1 runs timer 1, and TF0 it's overflow for timer 0 and overflow for timer 1. So we had left the discussion on these 4 bits. Now these 4 bits by default, all these 4 would be 0. Now if we need an edge triggered interrupt, okay, so there are basically two external interrupts as we know now. So this is port 3.2 is 1 and port 3.3 is 1. So if we want any of these two to be an edge triggered interrupt, then IT0 and IT1 should be turned on. So the previous code worked because all were 0, and when all the bits are 0, specifically if IT is 1 and IT 0 are 0, then this is level triggered. If these bits are set to 1, these interrupts become edge triggered. And when an edge triggered interrupt occurs, this is notified on the IE 0 for port 3.2 and IE1 for port 3.3. So this is about the edge triggered interrupts. You can try that as well. Now there's one more bit left with interrupts, and that is with respect to interrupt priority. Now there's a register called interrupt priority, and what it basically does is it polls the controller polls the 5 interrupt sources that we have, and then the priority is fixed depending on the contents or IP register. This you could check as well. So if there are any doubts or any suggestions, do let us know, and do share the videos. Thank you for watching.